we will continue with the course on optical engineering. In the last class, we looked at how we can start designing systems, and we took material with a certain refractive index and said what should its shape be such that we get a perfectly focused point image given a point object. So, we said in order to do that, in order to achieve that, we need, in this image, we need every ray of light that is leaving this source S over here to get imaged at this point P over here. Right? And the equation that satisfies or should be satisfied in order for that to happen is what we have written over here. This is nothing but the optical path length for every ray traveling through the system. So, we have written it for two rays over here. One is the on axis ray, so that is the ray traveling the distances S naught in medium N1 and Si in medium N2, and another ray from the same point, that is this point. It will travel through some point on the interface, and then it too should come to the same point P over here. However, it has traveled a distance L naught in medium N1 and a distance Li in medium N2. In other words, we are saying this should be a constant. And we went on further to say that there is such an interface, there is such a shape that will satisfy this equation. That shape is the Cartesian oval. Okay. Now, I can see a number of you wear glasses. I am wearing reading glasses. Do you think the curvature of those glasses, are they Cartesian ovals? No. So, somebody is saying no. That is right, they are not Cartesian ovals. Do you know what shape most lenses have? Convex concave is the nature of, so convex, I will say this is convex, this is concave. But if I had to describe this shape, is it a Cartesian oval, is it cylindrical, is it spherical, does it have some other shape? So, most lenses, it's not correct to say all lenses, but most lenses will be spherical. Okay. So, we have just said the best shape, the shape that ensures any ray of light coming from a point, object point, will get imaged to the same image point, is a Cartesian oval. And now I tell you, nearly every lens that we use does not have a Cartesian oval shape, but has a spherical shape. Why do you think that is? Sorry? Absolutely, it's easier to build. It's easier to manufacture spherical than it is any other shape. Today, we have very advanced technology where you can input a complicated shape and 3D print almost any shape. But the costs in mass production, 3D printing is not very good for mass production. So, the costs even today to mass produce something other than spherical would be very high. And of course, lenses and mirrors have been used in optical systems for centuries now. And we are talking about manufacturing requirements of the ability to manufacture these shapes hundreds of years ago. Spherical has always been relatively easy to manufacture. So, that might have been the reason historically people started with spherical shape. But even today, is for mass production, spherical shape would give you cheaper, it's cheaper to mass produce, and therefore spherical shape is used. Now, you have to think about this because we are saying the shape that gives me the best optical performance is something, and because it's not easy to manufacture that, I am doing something else. Clearly, the optical performance we get from this other shape has to be adequate or better than adequate. We are not sacrificing quality for ease of fabrication. Right? So, we are going to look at under what conditions does the spherical shape satisfy this equation over here. Again, I am not yet starting with the lens, I am just taking a single interface. Okay, so let us say I am right now going to start off by looking at refraction through a single surface. Okay, so that is my single surface, that is the optical axis. The difference is I am now specifying that this curvature is of a sphere. Okay, so if I were to continue this, I would actually draw a circle over here, right? Okay. This is medium N1, this is medium N2. The object I want to image is a point on the axis, let us say it is at point S, and of course there will be a ray that travels along the axis. There may be millions of rays. I am going to look at two rays, the one that travels along the axis and the one that travels at some other angle. We will call this distance L0 and this distance S0. S0 is from S to the vertex here. Let us say the image is at point P. So, this ray goes to point P, and this distance is Si. Because this is a spherical surface, there is a center of curvature C, and this line can be considered the normal to the surface, because this is nothing but the radius of this surface, right. So, in yesterday's class we said we define angles of incidence as the angle between the incident ray and the normal to the surface. So, this is now the angle of incidence theta I, this is the angle of refraction theta t, and we are going to need this. You will see shortly why I define this angle psi. Okay. So, let me see, do I have everything I need? Yeah, this point, let us call this point on the interface as A. Okay. So, the optical path length is N1 L0 plus N2, this is Li, but I can write L0 in terms of this triangle, right. So, I will have N1 L0 is R squared plus S0 plus R, this distance is again R, this whole squared minus 2R S0 plus R cos of psi. Yes, again just using some trigonometry here, plus the second part of this equation is N2, and now I am interested in this triangle. Right. So, that is N2 R squared plus Si minus R the whole squared plus 2R Si minus R cos psi to the power half. We are going to use Fermat's principle. Fermat's principle states that the path that light takes is the shortest path. So, I am going to minimize this path length. Shortest path here, we are deciding how this ray travels and reaches this point. If I were to change how it reached this point, it would basically be moving along this surface. In other words, this angle psi would be changing. So, the variable I am minimizing it with is d psi. Okay. We are using Fermat's principle. Okay. I am minimizing optical path length here. So, I keep the product n into L. unlike yesterday's example where we were minimizing the time, then I remove the refractive index. Okay. So, if I carry out this differentiation, I am going to have n1 by 2 minus 2r, S naught plus r sine, it will be minus sine. So, this is actually a plus. In the denominator, this entire square bracket is going to now go into the denominator. Remember that square bracket was nothing but the distance L naught, right. So, I will just put L naught into the denominator, plus n2, here I will have 2r Si minus r sin psi, but I will have a minus sign over here, and again I have a 2 in the denominator and I have Li in the denominator. Yeah. We are minimizing this according to Fermat's principle. So, we are saying this has to be equal to 0. Okay. So, if I cancel out this with respect to this 0, what I am going to be left with is n1 by L naught S naught plus r is equal to n2 by Li Si minus, and I can rewrite this so that I get n1 by L naught plus n2 by Li is equal to 1 over r n2 Si by Li minus n1 S naught by L naught. The equation in this form isn't, you are not going to look at this and say, ha, that really makes a lot of sense, right. You have applied Fermat's principle, you have got an equation. This equation is telling you something, but it is not at this moment telling you anything very useful. Why? Because the goal was to say every time a ray leaves the point S, I want an expression that tells me how that ray gets to P. And if I look back at this figure, I can see, or before I go back to the figure, if you look at this equation tells me every time I change the ray I trace. Now, when I change the ray I trace, what is happening? I am changing basically, if I change L naught here, if I change the ray I trace, I am changing L naught, which means Li is changing. But that means that equation, the right hand side is also going to change in order for it to be equal. So, if I trace another ray, if I put another ray, so I have a new L naught, right. S naught and Si have not changed because those are the points that S naught is the point I want to image. So, it should not change. But if I look at this equation, if I change L naught and Li, the only way this equation is going to stay constant is if I change S naught and Si. So, it does not seem useful at all to me, and we should not be too surprised because we have said the spherical interface is not the interface that satisfies the equation. So, it should not be surprising. But I started out this derivation by saying under what conditions can we use a spherical interface in order to give us imaging. So, in its present form, it is not carrying out the imaging that we want. Is there some condition we can apply that will make this equation work for us? And it turns out if you go back up to this part of the equation, you see you have a cos psi here. Now, what if I said I can make cos psi, or let us take the condition when cos psi is equal to 1. When would that be? What constraint am I now putting on the optical system if I say cos psi is equal to 1? I am now saying let's assume only rays making very small angles. So strictly speaking, if I say cos psi equal to 1, that means I say only on axis rays. But I'll be a little generous, I won't say only on axis rays, I'll say rays making a very small angle with the axis. Let's look at what happens to this equation if we only look at rays that make a very small angle with the axis. Does that help us? Now the moment I say cos psi is equal to 1, what will happen to my definition of L naught? L naught was r squared plus s naught plus r the whole squared minus 2r s naught plus r to the power half. Now I've put in, okay, so I should actually do this because I've said cos psi is equal to 1. But the moment I do this, I can see, let's expand this. So I have an r squared plus s naught squared so r squared plus r squared minus 2r squared, this and this cancel, and finally my L naught is approximately equal to S naught. And of course the same will happen for Li as well, it will be approximately equal to Si. If I now apply this condition to this equation, I have, so this is for the condition, cos psi is almost equal to 1, okay. Then I have n1 by s naught plus n2 by si is equal to 1 over r n2 minus n1. In other words, I've removed the L naught and Li, and I am saying any ray coming from the point S will reach the point P as long as the rays make a very small angle with the optical axis. Okay, we call such rays paraxial rays. This is also sometimes called first order optics or first order approximation, because we have made cos psi approximately equal to 1 and not to the 1 minus the next term, right. You can also do third order, higher order approximations, right. This is why the spherical surface is used. Yes, it's easy to manufacture, but it also gives us good optical images under certain conditions. What is the condition? As long as the rays are paraxial. This is now a very useful equation, right? And the right hand side of this is sometimes termed as relating to the focal length. So n2 minus n1 divided by r. So remember, your surface had radius of curvature r, and it had the mediums n1 on one side and n2 on the other, and we are now saying this surface has, in fact this 1 over f is the power of the surface, right. Power and units always given in meter inverse. The power of this surface is now determined by the refractive indices on either side of the surface and the curvature of the surface. Right. So if I want to change the power of the surface, these are the variables I have. I can change refractive index or I can change curvature. Now in a lot of cases, of course, one medium will probably be air, and you don't have an infinite basket of optical materials. So you can say, I want a material with this refractive index, and I'll go and pick any refractive index. You have a limited set of optical materials, so there are not that many refractive indices you can just pick up. So very often the variable you will be playing with is the radius of curvature. We want to change the power or the focal length of an optical lens or mirror. You will do that by playing around with its curvature. Now, this is still not that useful. Why? Because my lens, it doesn't consist of air on one side and then glass all the way, right? It has one surface, it has a second medium, and then that medium ends as another interface, and then I go back into air or I go back into some other medium, right? So, I now use this formula as a base. The image created by this interface will become the object for the next interface. That interface will see a certain radius of curvature, and it will have a medium of some other refractive index after it, and it will create its image. And I can now do this forever. The image it creates can become the image for the next surface, and so on. Okay. So, let us do that now and arrive at an equation for a lens, keeping in mind all the time that we are talking about paraxial optics. That assumption is not going to be explicitly mentioned again and again, but all of this works on the basis that you are saying cos psi is almost equal to 1. Okay? Okay. So, in order, oh yeah, and one more point, we talked about conjugate points also, and here we are saying S naught and Si, these are the conjugate points of this system. That means, in this particular example, I said, let us assume we want to get an image of the source at S, and we arrive at the image at P. I could interchange, I could put the source at P and I will get the image at S. Okay. So, these are the conjugate points of this system. Okay. So, that was the equation for a single refracting surface. Let us get the equation of a thin lens. As usual, I start with an optical axis. It is a lens, there are two interfaces. So, I am going to say this is one interface. Remember, it is part of a sphere or circle, and this is another . So, this is the lens. This is all that we are going to use. Okay. One side has radius of curvature R1, the other has radius of curvature R2. Okay. So, I have not drawn these properly. Please, these circles should be going, the optical axis is going through the center of the circles. This I call C2, the center of curvature of this circle, and this is C1, center of curvature of the first interface light will see. This has rad R2, this has radius of curvature R1, and let us say our object is sitting somewhere over here. So, this is point S. So, the distance of S from the first interface, we shall call it SO1, it is the first object point, right. The thickness of this lens, let us call it D. Right. And finally, let us say that the image is forming at P, but before it forms at P, there is an image formed by the first interface. Okay. And I am going to put that image over here, and I will explain why I am putting that image over here. Okay. So, light traveling from point S hits the first interface. If the second interface did not exist, in the case that I am setting up now, its image point would actually be at this point over here. Okay. And I will explain to you why I have done that. Okay. So, if this is the image point, whenever we are dealing with lenses, we always measure distances from the vertex of the lens. Okay. So, this is my first image, so I call it SI1. This image acts as the object for the second interface. So, the second interface, this is now object distance 2, and this is image distance 2. P is where the final image is formed. Okay. Remember, we had just arrived at this expression. Right? For a single interface. This was refraction at a single interface. Now, what happens in this expression? The left hand side is constant for a single interface. You are not changing the refractive indices, you are not changing the radius of curvature, it is a constant. Now, let us say I go on decreasing the distance S0. What does that mean? I go on bringing the object I want an image of closer and closer to the interface. Because the left hand side is a constant, what does that mean for SI? If I go on decreasing S0, it means SI is going to go on continuously increasing. At some point, S0 will equal N2 minus N1 by R. In other words, it is equal to this, or sorry, S0 is equal to F, not this. At some point, I can make S0 equal to F. What does that mean for SI? Where does the image happen if S0 is equal to F? That means SI is at infinity. What happens if S0 decreases further? What happens to SI? How will this equation get satisfied? It means SI is negative, or as he said, it will be on the same side as the object. And that's the reason why in this drawing I have put the first image formed on the same side as the object. Because if you think about it, by doing that, what am I saying? I have my object distance, and let's say S0 is my object distance. I have the focal length F, which is of the combined lens. Okay? I'm saying combined lens, I mean both the interfaces, but I have F1, which would be the focal length if there was only one interface. And why we do this is, this condition is almost always going to be satisfied. Two interfaces together have more power than a single interface, right? So, this condition is what you would expect, or is not surprising that this condition arises when you compare what's happening at one interface to what happens when you have two interfaces. Okay? So, that's why the first image I have kept it on the same side as the object. Okay, is that clear, that point? Okay. So, now I want to use the same equation that we arrived at for a single interface, but apply it iteratively, first for the first interface, and then the image that's formed will be the object for the second interface, and finally arrive at an equation for the full lens. Okay, so let's do that. So, I hope you all have this figure, because I am going to be using the variables from this figure. For the first surface, right, keep the equation in mind, right. So, I am going to have, and let me define this as the refractive index surrounding the lens as n subscript m. So that's true here as well. That's the medium surrounding the lens, and the medium of the lens I will call NL. Okay. In the first case, this is equal to N1 by my earlier definition, and NL is N2, okay, for the first interface. Okay, so I have Nm by S01 plus NL by Si1 is equal to NL minus Nm, and the first radius of curvature it sees is R1. That's the equation for the first surface, and the equation for the second surface, NL by S02 plus Nm by Si2 is equal to Nm minus NL by R. Okay, at this point I have to be very careful because I need to know what signs I am going to attribute or assign to each of these variables. There is a sign convention that we need to take into account. Okay, and the sign convention, and let me just go to this other. So, the sign convention I have given it to you, and I will share this with you on Moodle. So, do not worry about it too much now, but the first column is the sign convention that we are using with lenses. So, concentrate on this for the moment. What are the signs we associate with different parameters? What are those parameters? So, the parameters of interest are the focal length of the system, the object distance, the image distance, and the magnification. And you can see that for a convex or a converging lens, we will use the focal length as positive. Okay. For a concave lens, it will be negative. And in fact, we will keep coming back to this because I will add a few riders as we go along, but I think at this point it is enough to just give you this information. The object distance, and this is what you need to note because we need to use this information now. If the object is towards the left of the lens, we say that the distance is positive. So, typically, historically, optics has always been designed by tracing light traveling from left to right, and that is why here if the object is towards the left or is left of the lens, we say the distance is positive. If the object lies to the right of the lens, we say its distance is negative. The reverse is true for the image. If the image forms to the right of the lens, it is positive. If the image forms to the left of the lens, it is negative. Okay, that's really what's important for you right now. We'll come back to this, but keep this convention in mind. So, I have to be now careful with these distances. I've written out two equations, but this equation, this term S02, it actually is a sum of this term and this term, and I need to take the convention, the sign convention into account when I add up these two terms. Okay. So, S02 is actually going to be Si1 plus D, and what was the convention for the object? If an object was to the left of the lens, it was positive. So, S02 can remain like this, but Si2 is an image distance, and in this particular case it also lies to the left of the lens. So, by the sign convention, this is going to be negative. So, I will just write that here maybe. Object distance to the left of the lens is positive, image distance to the left of the lens is negative. So, this is what I am going to get following the sign convention. There are other conventions, and there is no problem with you using any convention. You just have to ensure that if you're solving or working out a problem, you stick to the same convention from beginning to end. And it's also good practice to state what is the convention you're using, especially if it's going to be different from this one, just so that it's clear. Okay? Okay. So, if I now take these two equations and I add them up, keeping in mind this sign convention, let's see what we get. So, let's take all the nm terms, 1 over S naught 1 plus 1 over Si2 equal to, and on this side I have NL minus Nm one term plus I have an L 1 over Si1 minus 1 over minus Si1 plus D. All I've done is add up these two, the equations for each of the interfaces. Now, to make this again a little more useful immediately, let's make an assumption that the lens we are dealing with is a very thin lens. So, for a thin lens, in other words, the thickness D is 0. Why is it valid to make this? Even in the morning class, I talked about geometric optics as being the regime where we consider lambda to be 0. And that's a valid assumption to make because we are talking about imaging objects much bigger in dimension to lambda. So, here again, if I say thin lens, how far away is the object from the lens? If we are talking about distances much larger than the thickness of the lens, with respect to the thickness, I can consider that distance so much larger, the thickness can be considered negligible. Okay? But the advantage of doing this is, if I look at the equation above now, if D goes to 0, this term here will disappear. So, with that condition, I can now say, and let's make some more assumptions. Let's say the medium surrounding the whole system, medium Nm is equal to 1. So, let's say it's air. I'll have this equation. I have an equation which is in terms of the object distance, in terms of the final image distance. The object distance S naught 1 is the location of the object on the optical axis from the vertex of the first surface. The image is the location of the image point on the optical axis from the vertex of the second surface, right? And the medium surrounding this lens is air, so I am not bothered about its refractive index, and the medium of the lens is NL, that appears in the equation. Both the radii of curvature appear in the equation. It's not very different from the equation we got for the interface, that also the power was a function of radii of curvature, radius of curvature. Here it's a function of both the radii of curvature. Okay. Again, this is called the power of the system, and often you will see it written in this form, where U is used as object distance and V is used as image distance. Okay. This if you write this in terms of u and v, it's also called the lens maker's formula. Sometimes this is called the Gaussian lens formula. Pretty straightforward. So let's just run through some possible scenarios here. But what happens now when the object is located at different places? Right? This is again high school optics. Right? But now you should have a little better understanding of where it's coming from. Right? If you go back to your equation, 1 over object distance plus 1 over image distance is equal to 1 over the focal length. If the object is at infinity, this term is disappearing, the image is happening at the focal length itself, right? And you can move your object from infinity to a position 2f away from the lens to something in between, to f, to less than f, and you can see how the image moves accordingly. Okay, and that's one of the first exercises you'll do in the lab, the simulation lab, is to simulate by changing object position where the image is forming, and also looking at the nature of the image, because mostly you may get a real image, but at some point the image will appear to be on the same side of the object, and then you get a virtual image. Okay, so I'll just scroll through these, but this is actually what you need. One of the exercises you need to do in the lab today is actually send light through a lens and change object position, and then monitor where the image is forming. Okay, and you can see this is the last case when the object moves to a distance less than focal length. The rays now, they're still of course going through the lens, but they are diverging here. They are not going to converge to a point. They appear to come from a point over here, and that's why we say it's a virtual image. It's virtual because we would see it with our eyes as if it was coming here, forming here, when actually the rays are diverging over here. You could not place a camera or a screen here and capture. You could not place a screen here and capture that image. You need extra optics to capture that image.